Iron ore is the backbone of global steel production and world holds over 170 billion tons of crude reserve. The largest share belongs to Australia, Brazil, Russia and China, the powerhouse of iron ore supply. When it comes to ore types, hematite stand out with 60 to 70% iron and low impurities, making it ideal for steel making. Magnetite contains up to 72% iron in its pure form, but mined ore is often lower grade, requiring beneficiation. Goethite found in tropical laterites offer 55 to 63% iron with moderate impurities. Banded hematite quartzite or BHQ is a low grade ore with 35 to 40% iron and high silica, demanding advanced processing. Other ores like limonite and siderite are mined far less for commercial use. Now, coming to our this important table, which summarizes the composition of main iron ore type. Hematite with the formula Fe2O3 contains between 60 and 70% iron, with silica ranging from 2 to 8% and alumina between 1 and 4%. It's India's main ore and is considered high grade. Magnetite Fe3O4 can have 60 to 72% iron in processed form, but like hematite, its silica and alumina contents are similar. It's often beneficiated in China and Australia to upgrade quality. Goethite COOH is a lower grade with 55 to 63% iron, higher silica at 3 to 12%, and alumina up to 7%. These ore type typically need beneficiation before steel making. Finally, banded hematite quartzite or BHQ has a very low iron content, just 35 to 45%, but extremely high silica, ranging from 30 to maybe 45%. It also contains 1 to 4% alumina and require advanced upgrading uh, techniques. Now coming to this slide, which compares the world top iron ore producing countries, their reserves and production characteristics. Australia leads with an enormous 51 billion tons of crude reserve and 930 million tons of usable ore in 2024. Its hematite and magnetite deposits are mined by giants like BHP, Rio Tinto, and Fortescue Metals, with most production shipped as direct shipping or DSO. Brazil follow with 34.6 billion tons of reserve with 440 million tons of usable ore, known for its high-grade hematite from the Carajás mines. Companies like Vale, CSN, and Samarco blend and carry out limited beneficiation. China has 23 billion tons of reserve and produces 270 million tons of usable ore with a mix of magnetite and hematite. Heavy beneficiation is essential due to lower grade ore. India's reserve stand at 7 billion tons with 270 million tons of usable ore only. Both hematite and magnetite are mined by NMDC, SAIL, Tata, JSW, and private players, with the limited upgrading facilities focusing on converting fines to usable forms. Russia, with 25 billion tons of reserve, producing 91 million tons of usable ore, mainly magnetite and hematite, upgrading for concentration and pelletizing. Iran holds 2.7 billion tons of reserve and produces 90 million tons, relying on concentration techniques. Lastly, South Africa has 1.5 billion tons of reserve and produces 66 million tons, mostly hematite, managed by Kumba iron ore blending ores to meet market need. Now coming to our next slide, uh, India holds substantial iron ore reserves split between hematite and magnetite. Hematite resources are estimated at 9.6 billion tons, while magnetite stand at 3.4 billion tons. So several major companies dominate mining in India. NMDC operates at Baladila. Similarly, all other mines are operating from their own epicenters. On the magnetite side, other companies and especially beneficiation project in Karnataka and Goa, upgrading lower grade magnetite into usable concentrate. Now coming to our next slide, about which is about the India's iron ore industry, is still dominated by high grade hematite with the iron content between 60 to 65%. However, magnetite, which contains only 30 to 35% iron, is also present and require beneficiation before it can be used in steel making. Increasingly, attention is turning to lower grade ore such as a banded hematite, quartzite, and fine particles, which need significant processing to meet blast furnace requirement. Upgrading efforts are gaining momentum. Many companies are doing of a similar sort of projects. Australia's ore is mainly high-grade hematite with some magnetite. Reserve quality ranges from 58 to 62%. Iron in direct shaping ore. Key players include BHP, Rio Tinto, and Fortescue Metal, and upgrading its limited to simple crushing and screening. Brazil focuses on high-grade hematite with iron content 62 to 66%. Companies like Wallace ESN and Samarco use blending and fines processing to meet customer specifications. China's ore is largely low-grade magnetite with less than 30% iron in raw form, upgraded to around 60% after beneficiation. So major company like Ansteel and Bausteel rely on magnetic separation and sintering to make the ore usable. India has both hematite and magnetite deposit. Hematite at 60 to 65%, iron and magnetite around 35%. Rasa's reserves are dominated by magnetite with raw iron content between 32 and 40%, along some hematite. Similarly, Metallo Invest and Sebastel and NLMK use concentration and pelletizing to enhance ore grade. Hematite from countries like India, Australia, and Brazil typically contain 60 to 65% iron with silica between 2 to 8% and alumina between 1 to 4%. This high grade profile makes it preferred choice for steel making. Magnetite, as mined in India and China, has a much lower iron content in raw form between 32 to 40% and higher silica ranging from 10 to 15%. Alumina is similar to hematite at 1 to 3%. To be used efficiently and effectively, magnetite must be upgraded to concentrate or pellet form. Similarly, BHQ found mainly in India and even lower in iron at 35-45%, as mentioned earlier, has extremely high silica level up to 45%. Alumina remains at 1 to 4%, and these ore require advanced beneficiation and pelletization to become suitable for blast furnace and direct reduction process. It begins with the crushing, the screening, first step to separate lump from fines, remove oversized material, and from there ore moves to wet beneficiation, a combination of a spiral separators, magnetic separation, flotation, and gravity concentration. These techniques work together to raise the iron content and remove impurities. In Australia, particularly Pilbara region of Western Australia, most iron mine is high-grade hematite, often referred to as a direct shipping ore or DSO, with iron content between 60 to 62%. This ore requires minimal processing before being exported. Brazil's story is similar. Hematite dominates production, especially from massive operations like Vale's Carajás mines, one of the largest iron ore mines in the world. Brazilian hematite also has high iron content and is primarily used for the steel making. Both nations do have deposits of magnetite, but these are far less significant in volume and export share compared to hematite. In its pure form, hematite contain up to 69 or rather 70% iron by molecular weight, and through commercially mined ore have slightly lower percentage due to presence of gangue mineral. By leveraging extensive reserve of high grade hematite, Australia and Brazil maintain their leadership as world's top iron ore exporters. Now, their mining operations are built around high-grade reserve that require little to no beneficiation, drastically lowering processing costs and speeding up delivery to international market. The Pilbara in Australia and Carajás complex in Brazil are not just rich in ore; they are logistical powerhouse with railway, port, and infrastructure dedicated to moving millions of tons of iron ore each year. By focusing on direct shipping ore or DSO, both countries can sell a product that really for the blast furnace almost immediately after extraction. This efficiency combined with vast reserve explain their consistent position as the world's leading supplier of high quality hematite iron ore. Hematite is relatively straightforward, and it's typically found as a massive form and is free from fine grained impurities. That means we can use simple physical methods like crushing and screening to process it. No fancy technology, just basic mechanical separation. It is efficient, low cost, and doesn't demand much energy. Magnetite, on the other hand, is a different story. To concentrate the magnetic material, we need magnetic separation, but before that the ore must be ground down to a fine particle size. Why? To liberate the magnetite from the gangue minerals. This step is energy intensive and require a more complex plant setup. Think advanced grinding circuits, powerful magnetic separators, and high operational costs. So while hematite is the easygoing cousin. Magnetite demands more efforts, but it also delivers a high grade concentrate that valuable for steel making. When it comes to processing iron ore, not all ores are created equal, especially when we compare magnetite to hematite DSO. So, magnetite ore demands more energy and capital. Why? Because it requires grinding the ore to fine particle and then using magnetic separation to extract the valuable minerals. These steps are resource intensive both in terms of power and infrastructure. Hematite DSO ores, on the other hand, is keep the beneficiation process entirely. That means lower processing cost, faster turnaround, and simpler operations. It's a direct shipping ore, just crush, screen, and ship. So let's explore the chemistry and the iron content of three major iron ores: magnetite, hematite, and goethite, and understand how their properties influence processing and industrial use. Magnetite boasts the highest theoretical iron content, around 72% Fe. Its a strong magnetic properties make it ideal for magnetic suppression. But here is the catch: the natural magnetic ore often contains only 25 to 40% Fe due to impurities. That's why beneficiation is essential to concentrate iron before it's usable. Hematite, now Fe2O3. So hematite comes close with pure iron content, around 70% Fe, and naturally occurring hematite ore typically range from 55 to 65 Fe. So it's the most abundant iron ore globally and often found as a DSO, coarse grain, low in impurities, and ready for use with a minimal processing. Coming to goethite, goethite contains less iron, typically 55 to 63 Fe only in ore form. It's common in weathered zones and often mixed with other oxide like hematite. While it's less iron rich, it's play a key role in super enrichment zones and still a valuable resources. Understanding these differences helps us optimizing our selection, processing strategy, and energy use in steel making. So